Okay, we've just got notice that we're on air. Okay, so it's welcome to our first masterclass of the day. We have 2 hours today, and it's a great pleasure of mine to introduce my former colleague at Imperial, but now department member here in DAMT, and a friend to many of us here. So it's a great pleasure to introduce Thanasis Fokas, who's going to survey several things he's been looking at in the last few years, and looking forward to it very much. Thanasis.
Thank you very much. Okay, so I will talk about these 3 topics. Essentially, they have nothing to do with each other. However, there is a commonality of complex variables. So this is the underlying
view.
other than me, the commonality of complex variables. And the reason why I chose these 3 topics is because I've been working on them for many, many years, but also because these were the 3 topics which were funded by my EPSRC senior fellowship for the last 4+ years. And that's why these last 4+ years have been kind of a dream life for me. EPSRC demanded from Cambridge to put me on a leave of absence, so even if I wanted to teach, certainly I wouldn't. Certainly I couldn't teach. And again, but there are many reasons why I'm happy to be here today. One is that this EPSRC fellowship, in some sense, was the fact that EPSRC perhaps was feeling remorses for not funding a project that Peter Clarkson, Darren, myself, and a couple of other colleagues put together. But for some reason they didn't fund it, and then my fellowship was after that, so probably they felt bad and funded mine. That's one reason. The second reason is in the audience there are 2 people that have been of crucial importance in my development as mathematician. See, I got my PhD at Caltech. My advisor was a great person, Paco Lagivstrom. But my real mentor really was Mark Ablovich.
Not true.
Mark really, so he was my true mentor. And with respect to the first topic I will talk about, which is this unified transform, nobody contributed more to its development than Alexander Ich, who is here. So it's really a great pleasure to discuss these topics in front of these 2 people. Okay, so I have talked about this before, and I always run out of time. So because I know that some of you will not be able to be here this afternoon, I was already told John, for example, has an appointment, and maybe I will tell you summary of what the second and third part are, and then I will concentrate on the first, because I expect the second and third part will be discussed this afternoon, in case you miss the afternoon. So, a lot of my work in the last 20 years has been on medical imaging. In medical imaging, we have worked on 2 different topics, one on electromagnetoencephalography, and this work was most done here in Cambridge, with various postdocs and collaborators, and we have a patent through the Cambridge Enterprise. So this part was not in my fellowship because of this patent. So I will not talk about this. But the other part has to do with positron emission tomography and with single photon emission characterized tomography. And when I started working on this topic, I also a center was created for me at the Academy of Athens, which now has about 10 people actually. And most of this most of the work of this center was on this topic. And this is what I will present this afternoon. You see, although I'm supposed to be an applied mathematician, I never chose a problem because of its practical implications. See, the main reasons for choosing the problem was always aesthetics and general mathematical importance. But I was very lucky because both of the problems I chose with respect to medical imaging, both electromagnetosphallography and positron emission tomography and SPECT, give rise to very beautiful mathematics. So I was very, very lucky with that. And but on the other hand, now both of them have very, very serious practical implications. They are used, and I will discuss a little bit about that. Now, the third topic is maybe the most interesting. This has to do with asymptotics of the Riemann Zeta function. I have worked on this for more than 10 years. At the beginning, I was keeping it secret because I didn't want my colleagues here to think that I've gone crazy. But finally, I had to start writing papers, so it was revealed. It started you see, at Cambridge, as you know, we have to give a new course every few years. And I first introduced a course on solitons, but then I have given a new course, and they asked me to give a course based on our books, based on our book, a talk on advanced complex variables. And the previous person was Stephen Siklos. And at the end of the course, he had something about the Riemann hypothesis. You see? And this reminded me of the Riemann function, and I had some crazy idea at the time. At the time, I was working full time on my method. And I thought there would be some connection, and indeed, there is some connection, which I will not even discuss because it doesn't give anything practical. But once you go into this, then it's very difficult to escape. So I stay in this, and we have some important results. You see, I will tell you the results after, but I will tell you the reason. You see, once you make contribution in an area that anybody who somebody has worked, you see, the best estimate, for example, up to now was due to Bourgain, late Bourgain. He did not even reach 1/7. You see, Hardy reached this famous exponent 1/6 for almost 100 years. People tried to improve this, but even Bourgain never reached 1/7. So we claim we have now 1/12. So how can you compete with these great people and have a result? I mean, so you always have to ask this question: what is your advantage, if any? You could never get something out of nothing. And as I will try to convince you this afternoon, we have advantages. You see, there are three advantages. One is the starting identity, which still I don't know how to motivate. I remember speaking to Atiyah, by the way, the reason why Atiyah, at the end of his life, returned to this after our discussions. And Atiyah asked me if I was happy with what I have done. I said, of course I'm not happy. For example, I don't know how to motivate my starting point. And he says, I will tell you, but of course he never did. It was very interesting, reminding of Gelfand, you see. This approach, we can do everything, it's a great approach. So we have a new identity, which is very powerful, I claim. Then we use asymptotics, which is completely new. And the third is we use all the estimates that the classic approach uses, but extended to double sums. So since you use new ideas and new tools, it's not completely surprising that you get new results. I will try to give you some details of that, but this was a very, very hard problem. I didn't expect it to. There were some errors in the process, but fortunately, now there are about 5 or 6 papers, either out or in press, and fortunately, none of these papers has errors. There were some errors in the papers which were put on the internet, but fortunately, there are no errors in the published papers. But let me start with the first topic, which was another surprise, actually. So, not everybody knows integrable systems, so let me begin maybe by, how do I advance? By this, I guess, yes? You're right, thank you very much. So let's start with integrable systems. You see, I mentioned already that Mark was really my true mentor, but the person who influenced most than anybody else in my life, even above Mark, was Israel Gelfand. And Gelfand asked me to explain to him what are integrable systems. See? At the beginning, I thought he was joking, because he has one of the many things that Gelfand has done is the Gelfand-Marchenko equation, which for many years was the basis of universe scattering until the Riemann problem was introduced. You see, and I thought he was joking, but of course he was not, because different people have different levels of understanding. I thought at the time that I understood integrable systems. After all, it was the only thing I was doing. So when he asked me in 1990, do you understand integrable systems? Of course I understand. He says, okay, then you can explain to me. And I couldn't explain to him what were integrable systems. The ones here that know integrable systems know that the basic property of integrable systems is this miraculous fact that a nonlinear PD can be written as the compatibility condition of two linear eigenvalue problems, which, because Peter Lax was the first one to appreciate it, is called the Lax pair. You see? So we push and push with Gelfand, but again, all the credit should go to the late great man. And finally, we came with something that should have been discovered by the classics, but it was not. And this was that linear problems also possess Lax pairs. Okay? So this is an example. So this is the linear form of the nonlinear Schrödinger. So you throw away the linear term, and then the claim is that this equation can be written as the compatibility condition of two simple equations. What I mean by that? Well, if I give you u, and I also give you ux, then you can solve this equation and find nu, yes? But also you can solve this equation and find nu. So in general, these two solutions will have nothing to do with each other unless there is some underlying compatibility, and you can check while I'm talking, it takes you a minute to check that these two equations will be compatible if and only if u satisfies this equation. So this is the essence of the Lax pair. Okay, which means that in principle you can forget about this equation, and in principle you should obtain any information relevant to this equation by imposing this alternative property. If you look at this looks like an OD in X, and this looks as an OD in T. So you can think of this as an advanced form of separation of variables. And it's indeed an advanced form of separation of variables, because although because such a thing is valid for integrable nonlinear equations for which the classical separation of variables fails. But if you do push the separation of variables, then you will look for solutions like this, right? And then you will see that each of them satisfies an OD. Okay? Of course, this is a very limited assumption. However, via spectral theory, starting from this separable system, you can have a rigorous theory to create solutions of this problem. And roughly speaking, what you do is by an appropriate spectral analysis of the X part, you can derive an X transform. And this is very hard stuff, by the way, to do. What you have to do is you have to find the Green's function associated with this, you have to integrate in the complex plane, and then you will pick up in the integration both the continuous and the discrete spectrum, and then there's a questionable things because you have to prove completeness. So this is a very hard job to do this, you see. But this will give you, if there exists, a proper transform for your problem. Okay? But look, now, and similarly, if you do the analysis of this, you will find a transform in T. You see? But now, so in terms of spectral theory, it's clear what happens. In terms of spectral theory, the operator you get from the X separability gives you an X transform. The operator you get from the T separability you give a T transform. But now, for the first time, because you have this compatible system, you can ask the question, what happens if I do spectral analysis, whatever is meant by spectral analysis, simultaneously? What kind of transform will I get? You see? And you get a new transform, which is this unified transform, or the Fokas transform. And of course, although this was how this at the beginning was derived, later we understood that for linear problems, you can avoid this construction, and you can do, for linear problems only, you can do everything without referring to like pairs, and this of course simplifies things. But for nonlinear problems, of course, this is the way to do it. So already you see that there is a very deep relationship between what I will tell you now about the unified transform and what we did with Gelfand in this paper. By the way, this is the only paper of my life that has been lost. It was lost for many years. So this work was done in 1990. But then it only appeared in 94 because the journal lost the paper. Lost it? Lost it. It was lost. But anyway, there was another fantastic implication of this work. You see, which is the following. Look, already mentioned to you that if you do spectral analysis and you analyze this equation, you will find an X transform. So for example, here, if you want to solve the problem on the infinite line and you analyze this, you will get Fourier transform. But similarly, if you analyze only this equation, you will also get the Fourier transform. But you see, this is a first order equation, while this is a second order equation. And this we understood with Gelfand, that it gives a new way of deriving transforms. And actually, if you do a problem in 2 dimensions, then you derive the 2D dimensional transform using a D-bar problem. And this derivation is very nice because it's not iterated, 2-iterated, 1-dimensional Fourier transforms. It's an honest 2-dimensional Fourier transform. And actually, in a part 3 course here, this is what they use to introduce Fourier transform. You don't need distributions, you don't need anything to do this. You see? And this is when we said with Gelfand, now, you see, we have a unified transform because for a linear problem, you use Fourier transform, but now Fourier transform can be derived through a Riemann-Hilbert problem. For 2-dimensional problems, you use the two-dimensional Fourier transform, but 2-dimensional Fourier transform now can be derived through a bar problem, and this procedure can be extended also to nonlinear equations. Okay? But you see, in the early 1980s, you see, this was after the heroic, as Zahar would call it, period of integrable systems. All the simple problems were solved. You see, everybody knew how to do problems in 1+1, namely how to solve the Cauchy problem for equations in 1+1, or the periodic problem, which, by the way, hasn't been solved yet. That's a different story. And I was very lucky to go to Clarkson there, and Mark always has a great advantage, every many people in this area, which is a good taste. You see, so Mark knew that the next thing would be a system C2+1, and working with Mark, indeed we were able to extend inverse scattering to 2+1. And then the obvious next problem is we had done 1+1, 2+1, 3+1 nobody could do, still nobody can do, you see. 0+1 were all these, we could do them, so the obvious question is boundary value problems. What do you do about boundary value problems? In 1982, I'm sorry, Julian Cole, the late Julian Cole, with whom I have a connection, he was the first student of my advisor, Paco Lagström, and I was the last, came to Clarkson and posed a problem which amounted to solving KdV on the half-line. See, and Potsdam, where we were at the time, it's a very cold place.
It's a cool place.
You don't have much to do other than work. You see, other than work, you work all the time. And when Cole posed this problem, I said, fantastic. Tonight I'm going to solve the linear KdV on the half-line and get some idea. And I was very much looking forward. I ran home and I couldn't do it. I couldn't do it, you see. And at Caltech, Jerry Witham had taught us an algorithmic way of how to derive a transform from first principles. You see, I used this, it didn't work. I was shocked. You see, I always tell people the difference between young researchers and older researchers is very simple. Young person, if you get stuck, you get very upset. Older person, if you get stuck, you get very happy. Because you realize that this is a possibility of something important, you see. But I was very young. I got very upset. I asked Mark, he didn't know. I started calling people. I called Joe Keller, I called Martin Kraskell, and I called Stackold. The only good answer came from Stackold. Untitled Chapter, Professor Fokas, this is not a self-adjoint problem. And usually, for non-self-adjoint problems, we cannot derive a transform. Which is the correct answer, of course. And I was so upset about this problem. I said, okay, I mean, I graduated from Caltech, the Mecca at the time of applied mathematics, not to be able to solve the boundary value problem for K division K, but not to be able to solve, a boundary value problem for a linear problem. It's pathetic. It's pathetic. So I left mathematics. I left mathematics and I did medicine. I did medicine, which was a fantastic investment. So I owe a lot to this problem, because if it wasn't for the problem, I wouldn't have done medicine. So I'm very grateful to it. But finally, I returned. But this problem always stayed in my life. And after 15 years, I started thinking about from 1982, and this paper, as you see, was written in 97. And finally, there was a breakthrough again. Alexander Itz played an important role there through something which he called master Riemann-Hilbert problem, and it was done for nonlinear surrogate. You see, nonlinear surrogate, the linear problem can be done by the sign transform, for example. So when I got the solution, I was for sure that when I take a linear limit, I would rediscover the sign transform. But I didn't. I discovered something new, which I will tell you now, and this is how I realized that this gives you a completely new way of doing linear problems. And since then, there are many applications of these linear problems, and that I can tell you in front of everyone that I believe it is a very strong statement, unethical, not to teach this method if you know it to undergraduates. Because it is no comparison with what they learn. They can implement it numerically, they can do many things. We're writing a book now with a colleague at Harvard with emphasis on this, so hopefully after this book, many people will use it. Okay, so let's see what is this whole method about. So to explain to you this method, I will emphasize some details. I will use the most simple boundary value problem one can imagine, which is the heat equation on the half line. Remarkably, and here you see talk about serendipity. When I first met Gelfand didn't know if I was good or bad. So Gelfand wanted to test me. So Gelfand tested me by giving me this problem. I don't know if I have told you this. He gave me this problem. He says, so I did this, you see, very fast, poor guy, and I came up with this solution. This solution, by the way, exists in there is no book on boundary value problems that doesn't have this solution. Okay, this is a nice solution because you give me initial conditions, I take the sign transform, I know this function, you give me boundary values, I know this, and then I do this integral over lambda. It's like a nice solution, you see? So I did this very fast, So Gelfand tells me, I remember like now, we're in Athens, I pick him up from the airport, he says, are you done? I said, yes, very happy, very proud, very proud of myself. He looks at me, he says, you've done nothing. You've done nothing, it's a strong statement, You've done nothing. Mark, this was his statement. You've done nothing. I was shocked. But of course, Gelfand was always right. Yeah? Gelfand was always right. In what sense, when you obtain this, you've done nothing? And this is very interesting because again it shows the difference between, you see that sometimes the problem with applied mathematics is lack of logic. See, it's not that we sometimes are not rigorous, there's no problem. If you are not rigorous, but you know you are not rigorous, you can correct it. But if you are not logical, then you cannot correct it. You see? So what happens here? When I derive this equation, I start by taking the sign transform of u, x and t, you see, for which I don't know anything. I don't know if it exists, I don't know its properties, I don't know if this integral makes sense, I know nothing. Yes? So everything I do is fantasy. Finally, following this fantasy, I come with this expression. Now, in this expression, everything is at my disposal because I know this, therefore I can control this integral, and then I can start doing rigorous analysis on this. Of course, if a priori my PD friends tell me, look, the solution exists, is unique, has all these properties, then what I do is of course legitimate. But without this a priori information, strictly speaking, the correct logic is you say, never mind how I came up with this, Allah gave me this, or God, but now the work begins. What does mean the work begins? Well, first of all, if I have sufficient analytical power, I can put this in proper spaces, and this then is a nicely defined integral. Now I have to show that this satisfies the heat equation plus this initial and boundary condition. You see? It is not immediately obvious by inspection that satisfies the heat equation because the tip dependence is not like the initial problem, which is e to the minus lambda plus I lambda x, but has this, but still, it is not hard, it's a line. Okay? Similarly, if I put t equals 0, this term goes, and then I see that by appealing to the inverse sign transform, there I use the inverse sign transform on something I know, I reproduce, if I put t equals 0, I reproduce my initial condition. Yes? So I have satisfied this and this. But what about this? I have also to check that if I put here x equals 0, this will give me this function. You see, I very quickly do it. I put x equals 0, and I get 0. You see? And surprisingly enough, all right, what does it mean? What does it mean? I mean, there are two possibilities. One possibility is that all the formulae in the all books are wrong, which cannot be the case because somebody would have picked up. Or I cannot do this. What does it mean cannot do this? You see, if I put here x equals 0, I take the limit of this when x goes to 0. Yes, it means I cannot put the limit inside the integral. There are two limits because it's another limit. So I cannot exchange the integrals, which is another naive way of saying that this integral is not uniformly convergent. Okay? Which of course, and this is the only thing for the young people, there are not many young, but there are a couple, the only thing that the young people should remember is that what I have demonstrated here has absolutely nothing to do with this problem. Any solution you will ever find through a classical transform will be non-uniformly convergent. Why? How is the transform derived? It is derived, as you remember, by doing the Green's function for which you impose homogeneous boundary conditions. So this solution is good, if you like, only if the solutions are homogeneous. Okay? So I remember that a Chinese first noticed this when I was teaching this course, and I panicked. I said, what do I do? What do I do?
Where were you teaching this?
I was teaching it at Caltech. You see, and I asked your friend, Alan Newell. You see, what do I do? And Alan gave the correct answer, which was go to the complex plane. You go to the complex plane. And this is what we do. This is what we do. So this is, by the way, this is not the only problem. So here are some of the problems with classical transforms. So lack of uniform convergence we already discussed. Because of this, not straightforward to verify the solution representation actually solves the given boundary value problem. And of course, not suitable for numerics. No numerical analyst uses representation, as you know very well, to compute. You see great stuff. And requires, you see, there is this man, David, with Peter Kriller, solved this problem using my method. You see, this problem, as you see, is not separable. The other thing is, if you don't know the transform, to go from first principles to derive the transform is very hard, while as you see here, everything is trivial, what I would do, you don't have to derive anything. But of course, the most important thing is, here is remarkable fact. Well, this is actually, if you add here ut plus ux, this is the correct linear problem for KTV, because as you know, the first order term is ut plus ux. We take it away when we do from -infinity to infinity, but you cannot transform it away on the half line. And if you try to do ut plus uxx equals 0, Mark always says, what about transforming t? Transforming t, static speaking, should go from 0 to infinity. I want to go from 0 to t. If you don't go from 0 to infinity, you have to play various games, which are non-equal, etc. But even then, if you have ut plus ux, you will have to invert the cubic. And this is horrible business. You see? But this, I'm most impressed with this problem. I claim that this problem, from 0 to infinity, look at this problem, cannot be done by classical transform. You see? Okay, so what is the alternative? The alternative is, you should always remember that beauty survives. You see? Beauty survives, and it's very good for us. that beauty survives. You see, this is, for the initial value problem, we have the integral mouse infinity to infinity, and this is the Fourier transform of the initial conditions. Yes? It's a very beautiful formula. That's it, that's all. The initial value problem of the equation can be solved with that. Can this formula be extended to boundary value problems? If that's the case, that's fantastic, because it's a very beautiful formula. And the answer is yes. You remember when we were talking about this? We were together. Very good. You see, we had done some work with Mark, something which we call a direct linearizing transform, which was an extended way of getting solutions for nonlinear problems. And I talked about this in Brown, and a great mathematician was there, Rafi Koifman. And Koifman says, oh, what you have is a nonlinear version of Ehrenpreis principle. You see? So the Ehrenpreis principle tells you that if you have a domain which is convex, bounded is not necessary, smooth is not necessary, but convex is absolutely necessary, then there exists a measure and a contour such that the solution can be presented in this form. But they do not tell you neither what is the contour nor what is the measure. And what is for me shocking, because pure mathematicians are so good in finding general results, they did not even find what I would call you now a global relation, which means they did not even postulate the relation which couples all the possible boundary and initial conditions. By the way, Koifman never told us that we need convexity. You see? And I tried to use with Beatrice Pellonis a problem which was not convex and we could not do it. And later we realized that indeed convexity is necessary. Okay, so now I'll give you the representation, the alternative to the formula you saw before, which is given by this formula. So, you see, always in this method, you have, so if you have a problem on the half line, you have what you had before, which was the initial value problem, plus something else. If you have a finite difference, plus another term. So here, we do it from 0 to infinity, so from half line problem. So we have a term which is what you would have if you were doing the initial value problem, where this is nothing but the Fourier transform of initial conditions, of course, now from 0 to infinity. Okay? But then you have a new term, and this new term reflects the fact that you're doing a boundary value problem. And now, this term consists of two parts. Consists of a transform of your boundary values plus the Fourier transform evaluated at minus lambda. Okay? And this is a generic form. By the way, note that this is, in the way written here, it is of the Ehrenpreis form. Yes, because the only xt dependence is in the form of the exponential, nothing else. See? Furthermore, it is now elementary in one line to prove that indeed, if I put here x equals 0, this is absolutely uniformly convergent. If I put x equals 0 in one line, you can prove that you reproduce this function. Okay? The only worry that you may have, especially if you are physically oriented, is causality, because you see this solution, as you see, this goes from 0 to t. And for an evolution equation, you don't expect the solution to depend on future data, because the problem was formulated from 0 to capital T. But and indeed, because of analyticity, you can replace this function by from 0 to T. Okay. So, but when you do things, if you do for physical and numerical considerations, it's better to use this representation. For proving things rigorously, it's better to use this representation. Okay, but before I tell you why this also numerically, by the way, when I teach this course to undergraduates, of course they immediately compute. Yes, immediately compute. This is another problem. One of the usual ways, somebody will ask you, how do we compute? Say, oh, now you have to take another course, etc. Now you compute in a figure way here. See, which is a great advantage, especially nowadays. See, MATLAB or anything, Mr. Alexander. But before I tell you how you compute, let me tell you the following. You see, this derivation is based on two ideas. The one is, the only transform you use is the half Fourier transform. You don't need to derive the transform, you don't need to do anything. Okay? What is the disadvantage of the half Fourier transform with respect to the sine transform? The sine transform, as you know, when you use the sine transform and you do integration by parts, you see, you kill because of the sine the unknown boundary value. Yes, so you remember you have the integral. Anyway, you understand. When you do integration by parts because of the sine, you have ux x0 sine of lambda x, and you have to evaluate this when x equals 0, and then you killed it. You killed your unknown. This is why the sine transform is good, you see. But if I use this transform, I don't kill this. I don't kill it. You see, so my transform seems that it has a disadvantage. Yes? Of course, just because it is so generic, it can be applied to anybody. But how can I get away from this difficulty? And by the way, if I'm doing KdV, not only I will have, if I'm doing linear KdV, not only I will have this unknown, but also have this unknown. So the situation looks horrible because I don't use the correct transform. So how can I make progress if I use the correct, and the answer is very, very simple. The answer is very simple. Please compare the half Fourier transform with the sine transform. There's a huge difference between these two. You see? This is defined only for lambda real. See? While this is defined for all lambda in the complex plane such that imaginary of lambda is less or equal to 0. Which means that this is an analytic function in a huge domain. So, question. Can I use the power of analyticity to determine the unknown boundary values? And the answer is yes. And this is why the method works. Okay. So this is the reason. So it is really an absolutely beautiful illustration of the power of analyticity. The transforms that we usually use cannot be extended in the complex plane. All right, let us continue, please. Will this come back automatically? Yes, it will. Very good. Okay, so let's see how do you compute. You see how you compute if in this previous representation you have functions for which you can compute their transforms explicitly, like the ones that we usually give to students, then all you have to do is an integral in lambda. Yes? Let's look at this integral in lambda. The integral, remember, it was formulated on this contour. On this contour, because I'm in the upper half plane, for large lambda, this decays exponentially. Yes? So the only difficulty I will have here is what happens for large lambda. But then I can even deform this contour, and if I go to this contour, not only this, but also this decays exponentially, so you don't have time to put the order, and you get the answer. And the students do it, and they love it because they get answers, etc. Even if you cannot do them explicitly, you see there is Matt Colebrook here who has made enormous progress in this. I will give him more and more credit later, but okay, that's it. Let's continue. Let me say a few words about the finite interval, because this is really an interesting case. Let me say things about the finite interval. You see, my method, never gives sums. Never gives sums. It's always integrals. You see, now that we're doing it, you see, if we do this problem on the half line, we have an integral along here, as already indicated. When we do it on the finite interval, there's an additional integral along here, but no sums. You see, no sums. Where are the sums? It turns out that in contrast to the case of the half-line problem, these integrals involve the integrands, of these integrals involve some denominators. But these denominators on these contours are bounded, as they should be. But these denominators have somewhere in the complex plane zeros. Where do they have zeros? At the usual spectrum, namely there. So what happens? In other words, in my opinion, what happens is that the traditional way of using series to solve boundary value problems on finite interval is by working at the worst possible place in the complex plane, because you work at the poles. You see? So I claim that for the heat equation, you have two ways to do it. You can either do it through integrals, or if you want, you can deform contours and pick up the poles. So you have an alternative. But then the big surprise happens when you do this problem. When you do this problem, now you have three contours. You have this contour, and this contour, which have denominators. These denominators have some zeros. The zeros are at the endpoints. Okay? So, no problem, everything is nice, etc. However, because my brain was polluted by the statement that if you do a problem of the finite interval, then you always have, if you do a problem of a bound domain, you always have discrete spectrum, right? I thought that this problem would do it on a half line, we must have a discrete spectrum. So this problem was done with Beatrice Pelloni. So I told Beatrice, okay, this looks very nice, but no problem, go do like this, do like this, do like this, and pick up the poles. So we'll have a sign representation. And she wouldn't do it, you see. So I thought, she's weak, but she's not weak, she's very good. I couldn't do it either, and now people have proven rigorously that this cannot be done. Which means that this ignoramus problem on the half-line, on the finite interval, cannot be solved analytically in terms of a sum. But of course, it can be represented in terms of integrals using this method. And by the way, there are many advantages. Everybody has done these Robin problems for the heat equation. You see, when then you have spectrum, but it's transcendental. Okay, here it's the same formulation. You don't care if it's Robin. You never have to look about this. Okay, let us go because let me say some things about the nonlinear problem. You see, this is one of our earlier works with Alexander Itz, which showed that this method is very efficient for computing large the asymptotics of the solution. So this is just to show off that we get very concrete information. You see, however, a problem that it's harder than this is when the boundary conditions do not decay for large t, but are periodic, which of course is more physical. And this problem was, many people got involved, Anne Boutin de Monvel, Alexander Itz, Pals, etc. And then we wrote a series of papers with Jonathan Lennox. And again, I don't think this problem can be tackled without these methods. And I'll give you an example of the power of this method. By the way, I'm revisiting these problems now with Maria Cristina, my student, but here is the problem. See, everybody knows for elliptic equations, you have a Dirichlet to Neumann map. Namely, if I give you Dirichlet boundary data, can you find Neumann? Okay? Of course, this problem can also be formulated for evolution equations, because for evolution equations, I can give you Q, can you find Qx? Okay? So here is a very, very nice problem. And I like very much problems which can be formulated very simply. These are the best. So here is a very nice formulation. I give you nonlinear Schrödinger, and I give you that that Q has a simple form. You see, two constants I give you, A which is real and omega which is real. Can you compute the Neumann data? And the answer is yes. Look at this beautiful formula. You see, omega is the same omega. For some values, others are more complicated, and C can be written explicitly in terms of this. This is a surprising result, and I don't think can be obtained in any other way. But just let me mention one more thing, since we're talking about. I mentioned before that in the historic period of integrable systems, at the beginning there was a lot of noise, a lot of excitement for two problems. One problem was the Cauchy problem of the infinite line, and the other was periodic index. And although periodic index, in my opinion, is not very physical, still it's a nice problem. And of course, for numerics, it's very important. And all the powerful mathematicians like Novikov, Manin, etc., did this problem. The first contributions were Alexander Eads, when they found the so-called n-gap solution. So what's n-gap solutions? As you probably have heard, integrable systems have n-soliton solutions. The question is, do there exist x-periodic analogs of them? And indeed, these are the solutions. And n-gap means that you have to go to a Riemann surface of genus n to obtain them. However, and everybody was happy that everything is great, etc. However, this problem is not really the solution of the problem, because these are only particular solutions. These are only particular solutions. The questions of density is complicated, etc. It's only particular solution. So the correct problem is like, I tell you, it's like saying that I have solved the Cauchy problem on the infinite line just because I'm able to write down the n-soliton solution. You should be able to have the solution for any initial conditions, not the initial conditions which correspond to the n-gap problem. And we worked on this problem with Alexander Eads in 2004, 15 years ago, and we made some progress. Namely, you see, in my method, when you apply this method to an integrable system, there are two broad classes of problems. There are some boundary conditions which you can do everything algebraically. And we have called these boundary conditions linear algebra. And there are some boundary conditions which you cannot. This one is not of that boundary conditions, which are much harder to do because then you have to analyze some which I call the global relation, which is a nonlinear equation. We proved with Alexander that the case of the x-periodic problem is linear algebra. So in principle, this problem could be done and should be done as effectively as the initial value problem. And indeed, we almost came up with a correct Riemann problem for doing this, but we didn't finish, and now I'm revisiting this problem. And I'm very hopeful it will be done. And it will be a contribution even in mathematics, because this would provide, in some sense, a formulation which, if you wanted to obtain through algebraic geometry, you would need a Riemann surface of infinite genus. So you will have, some sense, a representation corresponding to an infinite genus Riemann surface. Okay, let me say a few things, and I finish. Let me say a few things about elliptic problems. You see, when I derived this formula, I thought it was so beautiful that it was known. I derived this formula first for Laplace, but it was not. So let's look at, I will explain to you why it's so nice. So let's look at the modified Helmholtz. Modified Helmholtz because of minus. You have similar formulae for the usual Helmholtz, but slightly more complicated. So just look at the modified Helmholtz equation, that's why it's minus, inside a convex polygon. Okay? So what I want to do is I want to give you an integral representation for the solution of this. Of course, you can find the integral representation in the physical space, but I want to give you an integral representation in the spectral space. In other words, I want to give you N prime's principle for this. So what you do? On each side, you take an integral. So you go from Zj to Zj plus 1, and you have the Neumann boundary value and the Dirichlet boundary value. And you integrate with this exponential along the edge. So this is, if you like, your direct Fourier transform. Yes? So this is the proper Fourier transform corresponding to this problem. And then what you do, you take the inverse Fourier transform, look at this. This is exactly the minus of this exponential. However, now these are rays in the complex plane defined by this angle. So this is the correct M more than M price. I mean, this is M price form, but here I even tell you what is the correct measure. Okay? I first derived such a representation for the Laplace equation. I said it must be known. This is too beautiful, but it was not. Okay? Of course, you have a problem. What is the problem? This is not effective yet. Why it is not effective? It is not effective because in order to find u, I must know u hat. But u hat, as you know, not only involves Dirichlet, but also involves Neumann data. Okay? So how am I going to compute, if for example you give me Dirichlet boundary conditions, how am I going to find Neumann boundary conditions? See? The answer is always this method comes with the so-called global relation. So always this method comes with a relation which combines all known and unknown boundary values. And always this relation takes a very beautiful form. And here is the global relation. Here it is. You sum over this, and this must be 0 for all complex values of lambda. Okay? So question. How many unknowns I have? On each side, I have one unknown. Yes, suppose you give me u. On each side, I have one unknown. So this equation is one equation with little n unknowns. Can I solve it? Well, from the first question seems crazy. How can I solve one equation with an unknown? But the answer is, if you look carefully, it is one equation with its infinitely many equations, because lambda is arbitrary. You see? So since lambda is arbitrary, if then this, what you do, you expand this in any base you want, all right? So if you expand and you have n, capital N unknowns, this equation involves capital N times little n unknowns, and then you evaluate this in sufficiently many points, and that's it. And this is again the students do it, because Thomberg first did this, but we did better than Thomberg, because Thomberg was choosing these points arbitrarily. But we chose in certain rays, and by doing this, we brought the condition number, his number was 10 to the power 6 or something, which he told me is big, but no problem. Ours was something like 8. See? So students do this with great ease. Okay, so these are some reference about these hyperbolic problems. So this is the problem I already told you, the numerical implementation of Fokas method. Aston used this to obtain rigorous results for elliptic PDEs. And this is the paper I told you we did better in the sense that we chose these points carefully. And this was further improved in this paper with Mark, Matt Colebrook, with them extending this to non-convex domain. And then here, Matt did something which I never expected it would be done. Namely, you see, my method was always restricted to polygonal domains for elliptic PDEs and coefficients with constant coefficients, you see. But he was able to make this enormous extension to linear polygons and variable coefficients. Of course, these ideas have been used by many other people. This is a very, very incomplete list. See, we wrote, this was the last paper actually, we wrote together, Mark, which was already 2006. And the idea is very simple. The idea is, you see, the classical problem of water waves is what? It's Laplace equation, of course, with very complicated boundary conditions. But it's the Laplace equation. It means this method can be used, and we really provided a very, very, very nice formulation of this. This paper has already more than 100 citations, has been used by many people. Darren has used this very nicely. This is a very difficult problem, which again could be tackled by this network heat equation on networks. This, I want to say a couple of words. You see, my involvement with complex variables, and I finish. My involvement with complex variables began when I was a student at Imperial College in the aeronautics department, because my thesis, as it was a problem that had to do with acoustics. The idea was to put the fuselage above to minimize noise. And it gave rise to Wiener-Hoff problem. So then I learned Wiener-Hoff problems, and I realized that Wiener-Hoff problems was Riemann-Hilbert problem. So when I went to Mark and tried to do Benjamin Ono, and it was a Riemann-Hilbert problem, I told Mark I know how to do Riemann-Hilbert problems. You see?
Took a day,
Huh?
1 day calculation.
And however, I always want to come back to Wiener-Hoff problems, because I always thought that these problems can be done automatically through this method. And finally, we revisited this in this paper, because Anna is an expert in these problems, and this is, of course, a very, very nice new development. Earlier on, we had put together some simple formulation, but this shows you what? Shows you that if you do these Wiener-Hoff problems, once you go above scalar, the problem becomes very complicated. So complicated that you cannot even formulate most of the time a Riemann-Hilbert problem. First of all, even if you could formulate a Riemann problem, it is very, very hard to solve numerically, as you know. But with a new method, you don't have to formulate the Riemann problem. The global relation and this technique, which I showed you before, this technique provides you a very effective way to solve these problems. And this, I believe, it opens a completely new way in this entire area. And the last thing I want to say, which is not here, is that there's a large group of people now who use this method to prove well-posedness of nonlinear PDEs. Because as you know, for nonlinear PDEs, what you do is you look at the forced linear problem and then you iterate. But the forced linear problem, it's okay when you do initial value problems. But if you do boundary value problems, how do you solve correctly or properly or efficiently, for example, a forced boundary value problem for linear KDV? You see, this method provides a way to do it. So the first paper we wrote in this, it was with Himonas and Matsavinos in the assumptions of AMS, when we did KDV this way, but now there's an industry of people doing this. Okay. So as I expected, this would be what I was able to say this morning, and this afternoon I will talk about imaging, half imaging and half Lindelof. Thank you very much.
Thank you very much. We have a couple of minutes for questions. Mark.
If I go to the polygon problem, suppose I have the easiest problem, Laplace's equation. I would use Schwartz-Christoffel transformation, and I would say, well, there's a code, there's a Prof, there are people, and it works very effectively. Now, if you take very elongated polygons, we know there's crowding and whatnot. Presumably, your method gives these same results.
You see,
Is it easy to be Riemann mapping theorem?
You see, look, of course, but already you said the difficulty with, you see, Gelfand always, one of the many, many things that Gelfand thought was, analysis, something is important if and only if it generalizes. The problem with, as you already mentioned, Laplace, this approach to Laplace, is it will not generalize. You see? Remember, the reason why we did our stuff with water waves, many people were doing conformal mappings at the 2 dimensions, but what you do in 3, you see? And the same thing, what you do with Helmholtz, what you do with multiplication. But we did some comparisons with Schwartz. Schwartz, it's, in my opinion, is not a very effective way to do it. You work much harder than you should. But math maybe can say something. So number 1, it doesn't generalize. Number 2 is not natural. Yeah.
You mentioned Beatrice Poloni 2015 work with third order equation, and said she couldn't solve it using series representations. It's only because the numbers were the zeros of certain transcendental equation. If she, for instance, somehow somebody else solved
No. You don't have enough. You don't have completeness. You can't be solved. The claim is that there are now 3 different people who have proven the statement. It has nothing to do if it's transcendental or not. Transcendental is fine. If it exists, there is no problem. No. The statement is that this ut plus uxxx equals 0. There are 3 different proofs now. The analytical solution cannot be expressed in terms of a sum. End of the story. But it can be expressed in terms of units. You have to reboot reboot your brain. I had the same problem. There is a very simple, elementary, trivial, ignoramus linear problem, which, in contrast to what we know, to what we think, that bounded domains can be done through discrete spectrum, is not. Yeah.
I can comment on this.
Please.
So,
you have expertise on this, of course. Better than me.
Well, we wrote it together. the eigenfunction of the form a complete system. As there's somehow an eigenfunction with an eigenvalue at infinity, in some sense, which is the part that has to be picked up by the integral. So there's a paper from 2016 that we have on this, but I believe the first result that shows that the eigenfunctions are not complete goes back to 1915, 1916, around there.
Okay.
Can you comment a little bit on this recent work about variable coefficients PDA?
He should. It's not my work. It's not my work. A comment, if you like.
If you have a separable PDE, you could generate a global relation in the same way, and there are some numerical tricks to get it to
But
work.
it's still numerical, basically in some way it's
Yeah,
computational, that's enough.
it's all numerical as well.
Very good. Well, you know what? We've got another hour with Thanasis at 2 o'clock today, so please come back for that. But let's thank him and go to lunch.